Hello everyone. In this video, we are going to use Jamovi to help us out with our enhanced categorical section, specifically in helping us do a chi-squared goodness of fit test, a chi-squared test of homogeneity, and a chi-squared test of independence. So let's go ahead and look at our scenario, and let's go ahead and dive in. So here we go. A recent national report states that the marital status distribution of the male population age 18 or older is as follows: never married 32.4%, married 54.9%, widowed 2.4%, and divorced 10.3%. The table below shows the results of a random sample of 1,676 adult men from California. Test the claim that the distribution from California is as expected at the alpha 0.01 significance level. Okay, so what we're essentially doing is we're saying, hey, we have this like marital status distribution for the nation, and we want to know is, does California follow the national averages? Okay, so what we can look at is we have these national ones, and what we can do is we can take this like frequency and multiply it by the never married percentage, and we can see what we would expect to see if California actually was what we thought. Oh, sorry. We would take not this frequency. We would take the total number of people that we in fact saw, and we'd multiply it by the percentage of the national average. And this is what we would expect to see if California in fact follows the national distribution. The cool thing is, though, is that Jamovi will do this all for us. So what we can do is if we just go and click data, and let's go ahead and copy our data here, and let's paste it into Jamovi. Okay, we got, for some reason, two columns here. I think it's all duplicated. Let's go ahead and get rid of this B column. Let's delete it. And let's go ahead and we'll rename this, and we'll rename it to just status. And let's go ahead and do our analysis. So if we go to our analyses, and we go ahead and click on frequencies, we have this chi-squared goodness of fits under our one sample proportions test. Let's go ahead and grab it. We're going to bring status over as our variable. And then notice how it has, let's go ahead and give us our expected counts. It'll give us our expected over there. And now it gives us these proportions. Now, the baseline assumption is that they are all uniformly distributed, so we have the same number of married as the same number of never married, but that's not what we were given over here. And we can actually change these to get the ratios correct. So for never married, let's do 0.324. For our married, we can do 0.549. For our divorced, we can do 0.13. And for our widowed, we can do 0.0. Now we have these proportions down. Now we have the expected for what we would expect to see if California is following the kind of like US marital distribution for adult men. Okay, so what we can do is these counts over here for the expected should match up over here. So if we look at our never married, should be 543. That one checks out. Married, 920. That one checks out, and so on and so forth. So we can grab those expected counts and pull them over. All right, so the correct statistical test to use is this goodness of fit. And the null hypothesis here is that the distribution of the marital status in California is the same as it is nationally, or that California follows these national marriage distributions. And the alternative is that, well, maybe California is different, but our alternative is that the distribution of marital status in California is not the same as it is nationally. Next question, degrees of freedom. We look at the different number of levels that we have, and we minus one, so that gives us a degree of freedom of 3, and it goes right there, 3. The test statistic is going to be this chi-squared, and it's this 1.26, 0.26 right there. And let's go ahead and go down, and then the p-value is this 0.73, 73, 775, 78, yep, they'll match out. The p-value is way greater than our alpha, so based on this, we would fail to reject our null. All right, so in conclusion, well, what do we get to conclude? Well, we conclude that there is insufficient evidence to conclude that the distribution of marital status is not the same as it is nationally. So, like, we did not have enough evidence to reject this null hypothesis. So, our evidence, we basically get to go along with the basic assumption that because our evidence doesn't say otherwise, we're going to continue with the assumption that California follows these national values. Okay, so let's go down and look at question 2. let's go back to our data, and we're going to just clear out our data so we have a nice blank slate. And we'll clear out our results. And let's look at our next example. Okay, so here it says a fisherman is interested in whether the distribution of fish caught in Green Valley Lake is the same as the distribution of fish caught in Echo Lake. Of the 351 randomly selected fish in Green Lake, we have this certain distribution of fish. And if we look at the 523 fish caught in Echo Lake, we have another distribution of like rainbow trout, other trout, bass, and catfish. Okay, and then we're going to conduct this hypothesis test. Okay, so here, unlike before what we were saying is like, hey, we're looking at California and we're comparing it to this national average, these known values. Here, what we're looking at is we're looking at two different groups and we're saying, do the two groups have the same distribution or not? Okay, so in order to do that, that is going to be a test of homogeneity. Let's go ahead and grab our data and let's bring it on over. So I'm just going to go ahead and copy in our data and let's paste it into Jamovi. Okay, and let's rename these as A will be that as location. And then B, let's just label that as like fish. Perfect. Okay, so the null hypothesis here is that the distribution of fish is the same for Green Valley Lake and Echo Lake, that they have the same distribution of these different types of fish. And the alternative hypothesis is that they're not the same, that they have some different distribution. So let's go ahead and see how we go and do this. So let's go to our analyses. And we're going to go to our frequencies. And we're going to do this independent samples. Now, just conceptually, homogeneity test and the independence test mathematically are the same. But how they're set up is slightly different, and I'll get into what the differences are when we get to our independence one. But for this homogeneity, just remember that we are looking at these distributions of two different samples, and we're comparing the distributions to one another. Okay, so let's go ahead and grab our independent samples, and we are going to put location. Let's just put location as our rows, and fish as our columns. And we have our breakdown right here. And what we are looking for is our test statistic for this is going to be our chi-squared, this 14.515. The p-value gives it to us right over here as well, this p. And we get 0.0023, excellent. We get our sample size over here, that's good to have as well. And now we have this, that this p-value is less than or equal to, well, it's less than our alpha. Our alpha up here, we set it at 5%, and this is much smaller than 5%. Okay, so based on this, we would reject the null hypothesis. And so our final conclusion is that there is sufficient evidence to conclude that the distribution of fish is not the same for Green Valley Lake and Echo Lake. Now, when you do that, you also might want to say, it's like, okay, which ones look like that they are really, really different? And we can look at a couple things, like if you wanted to look at like some, not these, let's go look at our cells. We could look at like the percentages of the rows. And we can see like maybe which percentages are the biggest difference. We see like there's a pretty big difference in our catfishes between the two lakes, and there's a decent difference between our rainbows. The other look pretty close, and the bass look pretty close to each other too. But that's a quick way that you can see which distributions are kind of different from each other. There are also some plots that we could look at. Like let's look at a bar plot real quick. If we just click on this guy, let's see what it gives us. Hopefully it pops up. Yeah, so sometimes it's nice to be able to just visually see kind of these distributions. And instead of doing the counts, let's do the percentages, because it's going to be a little bit easier to see the differences between these two groups. So if we look at these percentage differences, we can see that like the rainbow looks like there's a pretty big difference. And there's, decent difference between bass, between the catfish. The purples look close-ish, and the greens look close-ish. Anyhow, it's just another way that you can actually look at those. let's say, oh, this is a better way to look at it. So that was percentages of the total. Let's look at percentage within the rows on our plots because that's what we really want to see. And there we go. Yeah, so we have these kind of big differences here. The greens are really close, the purples are really close, and these teals are quite a bit different. So anyhow, if you want to like graphically see what we did the comparison with the percentages, you can go down to bar plot, you can go to the percentages and within rows. And it's a handy dandy little bar plot that shows you what you're doing. So you could do side by side, or if you want to do stacked, you can, but stacked I always find is a little bit trickier to read, but you can look at it like that as well. I'm going to go back to my side by side. Okay, so that is how we would do a test of homogeneity. Let's do one more. So the last one that we're looking at is going to be this question 3. So it says a researcher is interested in investigating whether a living situation and pet ownership are independent. The table shows the research of a survey. So let's go ahead and clear out our data one more time. Go ahead and grab these, and I'm just delete those variables. Okay. Delete all of our analyses that we just did. Let's go ahead and grab our data. I'm going to grab the data, copy those, and paste them in here. Paste. And let's name our variables. Let's call variable A. Let's do status. And we'll do the next one as animal. Okay. So the difference between what we did here and with the fish in the lakes. The fish in the lakes, we knew what those two groups were, and we went and specifically looked at one lake and looked at the distribution of fish in that lake. Then we looked at the other lake and looked at the distribution of fish in that lake. Here, what's different is that we could do that. We could look at people who are single or a family or a couple, and then we could go in and see, okay, what's the distribution of like animals in single, what's the distribution of animals in family, and what's it in couples. We could do it, and that would be a test of homogeneity. But a test of independence here is what we're going to do is we're just going to go out to a bunch of people and we're going to ask them, what's your family status? Are you in, family? Are you just a couple or are you single? And what animals do you have? Because we're doing it like that, where we're not really like looking at the groups and then looking at the distribution within the groups, here we're just kind of getting it all in this jumbled kind of mess. This is a test of independence where we're saying, is there some connection or correlation between the different groups and the like animal status? Okay. So because of this, we are going to be doing a test of independence. So the null hypothesis here is that pet ownership and living situation are independent from one another, or there's nothing that's linking them together. And the other one is that pet ownership and living situation are dependent. And when that means it's like maybe couples are more likely to have dogs and families are more likely to have various or something. That would be that there is some connection or that they are dependent upon one another. Okay, so we've got these in, we've got status and animals in, and let's look at what we'd actually have to do. Let's go click on our analyses. Let's go click on our frequencies. And just like we did with homogeneity, we're also doing this independent samples. Okay, again, let's toss in status as we'll do that to the rows, animals to the columns. Okay, and we can look at our test statistic. It is this 22.025, just like that. Now, I want to show you, it doesn't matter which status or animals you do. Let's flip them real quick. Pop that out. Let's make status go to animals, and we'll make animals go to rows. And so let's say that you had flipped it from what I did. Notice how the chi-squared is still the same. Okay, so we've got our p-value is 0.002, just like we got over here in Jamovi. And then our p-value is less than our alpha. Based on this, we would reject the null. And so let's look at our conclusions now. So our conclusion here is that there's sufficient evidence to conclude that pet ownership and living situation are dependent, or there's some connection between them. Let's take a look at what this might be. Like we did with homogeneity, let's look at let's look at like our row percentages real quick. So we could see it's like, okay, are these cats? So if there was like no if there's no dependencies, I would see like the cat percentages and the none and the various and the dog, like they should see some similarities between all of them. Let's look at a bar plot. Like, this is probably going to be the easiest way to help us out. Let's do a bar plot and let's do percentages. Okay, so we see the cat as kind of goes down like this. We see none, we see the various, and we see dogs. And if there weren't any dependencies, we should see basically like the same thing going along. So let's go ahead and instead of looking at rows, let's look like total. You can look at a couple of these. Is it changing at all? There we go. There's within the columns. Let's do the total real. Okay, so because we don't see like these similar patterns between each of these groups, it kind of helps us see that we are having different distributions, like there's some connections between them. Let's go ahead and let's see if we can't flip these around. Let's change this to put, yeah, okay, so here's the single, the family, and the couple. So if we didn't have any connections, let's see, the single distribution of like cat, none, dog, and various should be the same between each of these groups. Now, if you notice, it looks like that single is like are likely to have either a cat or a dog, but like various is actually kind of low, and none is kind of low. And then if you look at the family or the couple, like couple looks like none is kind of high, and anyhow, it just these shapes are not the same. Because those shapes are not the same, that's kind of graphically showing what this chi-squared test is inferring. That there's sufficient evidence to conclude that pet ownership and living situation are in fact dependent. So anyhow, now that we did that, we have done an example of how we can do a chi-squared goodness of fit, chi-squared test of homogeneity, and a chi-squared test of independence. Best of luck on doing your enhanced categorical analyses on your own.